In addition to the rational roots theorem are two others, the irrational roots theorem and the imaginary roots theorem. And these allow us to find, if we know one imaginary root or one complex root, we can find additional roots. The key word here is conjugates. Conjugates. And what conjugates are, they're not opposites. All right? They're not opposites. But basically you have A plus B, and you would have the, not the opposite, but A minus B. These would add up to give you two A's, but the B's would eliminate. So if we're talking about imaginary numbers, we would have A plus BI and A minus BI. These are called conjugates. Conjugates. The A value is the same, the B value is the same, but we just have the inverse operations here. If we are talking about radicals, about irrational roots, we would have the same idea, just with it being the square root of b instead of b times I. So with the irrational roots theorem, I may say if the square root of 3 is a root, then you can say, then so is the opposite of the square root of 3. If I say 2 minus the square root of 3 is a root, then so is 2 plus the square root of 3. If I say 6 minus the square root of 7 is, or 6 plus the square root of 7 is a root, then I know that 6 minus the square root of 7 is also a root. Think about all of our answers when we solved quadratic equations. When we solved quadratic equations, if we had an irrational answer, it was the opposite of b plus and minus the radical b squared minus 4ac, and then all of that divided by 2a. So whenever we have a radical, we have its conjugate included with that. So if we had 6 plus 7 radical 2, or 6 plus radical 7 all divided by 2, we also had 6 minus square root of 7 divided by 2. All right? Those are conjugate pairs. Conjugate pairs. Now, the same is going to be true for our imaginary roots, because we had solved some quadratics such that we would end up with an imaginary component. All right? If we have an imaginary component, then we know that the conjugate is also a root. So if I say, if 2i is a root, then so is the opposite of 2i. All right? If I say negative 1 plus 2i is a root, then negative 1 minus 2i is also a root. Notice how these are not opposites of each other. The same a value, it's just that our b value has a different sign, plus 2i versus minus 2i. All right? If I have positive 7 plus 6i, all right, I could have positive 7 minus 6i, would also be a root. This allows us to, if we know one root, we can find another. All right, we can find another. So the conjugate pairs are the key. All right, so here's an example of how this works, and it can be something kind of simple. So for example, if I said, I think we did 2i and negative 2i. If those are my two roots, then we know that x minus this number and x minus that number would be factors of our polynomial. All right. So if I'm told to write a polynomial that has zeros at those values, I can write it like this. Now, if it's just x minus this and x minus that, this is pretty easy to do if we use FOIL. Watch what happens when we multiply conjugates. All right, x times x gives us x squared, x times 2i gives us 2i x's, negative 2i times x gives us negative 2i x's, and negative 2i and positive 2i make negative 4i squared. Now, we know that I squared is equal to negative 1, so we have negative 4 times negative 1, that means we have a plus 4. All right? Now, notice this, though. What happens here? 2ix's and negative 2ix's cancel out, okay? They sum to 0. So this adds up to nothing. This gives us x squared minus 4i squared, so x squared plus 4 is equal to 0. Now think about this. If x squared plus 4 equals 0, if you're to solve this, you would subtract 4 on both sides and then take the square root. The square root of negative 4 would be plus or minus 2i. All right, so this will account for both of our solutions. Both of our solutions. Whenever you have one imaginary root, you have its conjugate as another root. All right, so that should be helpful. What I want to show you, and the same is true as if we have, the square root of 3 and the opposite of the square root of 3. We could say, all right, well, x minus that radical times x plus, or x minus the opposite of that radical would equal 0. When we FOIL this out, when we multiply conjugates, there are some terms that cancel each other out. That's kind of the joy of working with conjugate pairs. All right? And so I'm going to do this. X times x gives us x squared. X times radical 3 and x times the opposite of the radical 3, those will sum to 0. And then I have the opposite of the square root of 3 times the positive square root of 3. That's just going to give me negative 3. All right, now think of this. If I'm going to solve this equation, I'd add 3 on both sides and take the square root. I'd get positive or negative square root of 3. All right, so writing the polynomial from the roots, following what we did in example 6.2, around there, maybe it was 6.4, I think it was 6.2, 1 or 2. Given the roots, we can write the polynomial in its factored form or in its standard form. Here's where it gets complicated, and this is where you're going to have trouble, all right? Because here we know one of the roots and another root, but there's going to be a conjugate here for this. So it's not just 3 minus radical 2 and 6 as our roots. We also have 3 plus radical 2. Sometimes you have to fill in the blank. All right, you've got to fill in the blank there and say, this is going to be another root. But if I'm going to write an equation with these roots, then I'm going to have to do some fancy pants algebra. All right? So if I'm writing a polynomial function, that means f of x equals or y equals, however you want to write that. Now, I'm going to use a bracket here. Because for my first pair, I'm going to take x minus this. All right, and I'm going to leave it like that. Then I'm going to take x minus this. All right, and then for the last one, x minus this. This is probably a little bit easier. Okay? So y equals x minus this mess times x minus that mess. These are conjugates. All right, notice how this sign isn't different. It's this sign in between here that's different. And then x minus 6. So this is cake. This is a little bit complicated. I threw on the minus 6 there so that you, or the x minus 6 there so you see kind of how this all plays out. But watch what happens when I multiply these. Okay? Now keep in mind, I'm going to do just FOIL here. So I'm going to multiply x times x first. It's going to give me x squared. Then I'm going to take x times negative 3 plus radical 2. All right, so minus x times 3 plus radical 2. The inside terms, x times the opposite of 3 minus square root of 2. So minus x times 3 minus the square root of 2. Then I've got to multiply these. A negative times a negative is a positive. 3 minus radical 2, 3 plus radical 2. All right, and I'm kind of running out of space, so at the end of this line I have to multiply by x minus 6. All right, I'm going to close those brackets and x minus 6. That's probably off the camera. Don't worry about it. You know that we're multiplying by x minus 6, so sorry about that you can't see it. If you're paying close attention, you should be okay. All right, now, looking at this monstrosity, I know that this is tough, but be patient, be patient. You can handle all of this multiplication. I'm going to do some distribution in here, multiply by the opposite of x, multiply by the opposite of x, and then FOIL that grossness. All right? This gives me x squared minus 3x's minus x radical 2, so that's this. Now I have minus 3x's again, but I have a negative x times a negative radical 2 that's going to give me a plus x radical 2. Notice that these are going to cancel out. That's not a secret. These are going to go away so that we don't have any radicals when we're done. Okay, I lost my train of thought. Here we go. Now I've got to multiply those. Now, we saw earlier that when I multiply conjugates, all right, my middle terms go away. So it looks like I just have this squared minus this squared. Okay, so what that looks like is 3 times 3 gives me 9. All right, I've got plus 3 radical 2. I've got a minus 3 radical 2. And I've got a negative times a positive, so a negative radical 2, that makes radical 4, which is 2. Okay, so I've got that. And then all that times x minus 6. Remember, there's an x minus 6 over here. It just kind of went off the camera, so sorry about that. Let's combine our like terms. All right, I'm going to use a different marker here. This and this, negative x radical 2, positive x radical 2, those will sum to 0. Positive 3 radical 2 and negative 3 radical 2, those will cancel, those will sum to 0. All right, so I'm left with, and let's look at my like terms here, y equals, all right, x squared minus 6x plus 9, plus 9 minus 2. So plus 7 multiplied by x minus 6. All right, this complex craziness became something that was a lot more manageable. Became something that's a lot more manageable. We can multiply that out. I'm actually not going to finish this. We're going to go from there. Or I'm going to leave it like that. But we can multiply that out and get our x cubed, right? Because we have 1, 2, 3 roots, so we should have an x to the 3rd power. Now here's what I want to do. We should finish that. I'm just not going to. I trust that you can if you've seen the other videos. What I want to point out is this. This will equal 0, or this thing will equal 0 when x is equal to 6. When does this equal 0? Well, it will equal 0 when x is 3 plus or minus the square root of 2. All right? So we can solve this using the quadratic formula, or we can say this equals 0 using quadratic formula or completing the square. And the approach that we could take is the opposite of b plus or minus the square root of b squared minus 4 times 1 times 7 all over 2. Keep in mind the opposite of b, so 6 over 2, that gives us 3. All right? And then b squared is 36. 36 minus 4 times 1 times 7, so 36 minus 28 gives us 8. All right? Simplifying 8, the square root of 8, we're going to get 2 square roots of 2. All right? 2 square roots of 2. But my 2's cancel out with the 2 a's that are in the denominator, right? So I should have 6 plus or minus 2 radical 2 over 2. If I simplify this, that gives me 3 plus or minus the square root of 2. All right, so those are my 2 roots. Okay, now, since you guys want me to, I'm going to go ahead and finish multiplying this out. I just had to explain how this connects to what we have here. All right, so let's do that multiplication. We've got x to the 3rd. We've got minus 6x squared minus another 6x squared. That's minus 12x squareds. I have a 7x and a positive 36x. So that's going to be, did I do that right? Yeah, 7x and a 36. That's a 43 x's. And then negative 42. Okay, so x cubed minus 12x squared plus 43x minus 42 is the polynomial that has these 3 roots, all right, these 2 that were given plus the conjugate of the irrational root using the irrational roots theorem. This is the polynomial function that has those roots. Now, we could do the same thing with, if this were, instead of the square root of 2, if it were 2i. 3 minus 2i, 3 plus 2i, and 6. It's still going to work out very similar. You're going to have some different signs in here. But for the most part, I think that you'll be quite happy with how all of that plays out. So yeah, that's the irrational roots theorem and the imaginary roots theorem.